All right, we're going to do the second portion of the area of triangles formula, and this time we're going to talk about Heron's formula, and we're going to do its proof, which is quite lengthy. So here we go. So Heron's formula. And this is with triangles when we have side, side, side. Okay, three sides of a triangle, no angles. We're going to need a few things. So let's already do a little sketch so we know what we're talking about. Any triangle, right? It doesn't have to be a right triangle. So we're going to have A, B, and C. No angle. So we have side B, side A, side C. Those are given to us. And we're going to be looking for the area. And again, just like part one of the video, I'm going to call area K here. We're going to need a few things to be able to do that. And here are the things we will need. We will need the formula. So for the area K of a triangle. And in the previous video, we said this is 1/2 A times B sine of angle C. We will need the law of cosine, which we know to be C squared is equal to A squared plus B squared minus 2AB cosine of angle C. We will need the semi-perimeter of a triangle. Perimeter will be just adding all the sides together, right? So if I want the semi-perimeter, that means half. Well, that would be, I'm going to use the letter S for the perimeter, or the semi-perimeter. That would be 1/2. All the sides added together, right? So A plus B plus C. We will need the Pythagorean identity. And here I'm talking about A squared plus B squared equals C squared, but I'm talking about the trig Pythagorean identity, right? So I want sine squared of angle C plus cosine squared of angle C is equal to 1. Now, this is not particular to angle C, but notice how I have angle C in the area formula right there. I have angle C right here in the cosine, law of cosine, and so I'm going to stick with angle C here as well, just so they're all matching. And now we're going to go back to some algebraic factoring knowledge that we need to recall. So the first thing we need to recall is the difference of perfect squares. And the difference of perfect square, and here I'm going to use X and Y so that I'm not getting, too mixed up here with all the letters with A, B, and C in there. So I'm going to stick with X and Y for the factoring here. The difference of perfect square is that when I have something squared minus something else squared, so X squared minus Y squared, I can factor that as the conjugates X plus Y times X minus Y. Okay, so we need to remember that. And then the other special rule of factoring, we want to remember perfect squared trinomials. And this is, and again, I'm going to stick with X's and Y, and this is when I have X plus Y quantity squared. This will factor as X squared plus 2xy plus Y squared. And if I had the subtraction of that, it would be x minus y quantity squared, and that would then be x squared minus 2xy plus y squared. Okay, those are all the things we need to remember, and we already know all of that. We have learned that. So now let's see if we can put that in action and do the proof. So we're doing the proof of Heron's formula to find the area of a triangle when we have three sides. And Heron's formula says that area K is equal to the square root of the semi-perimeter times the semi-perimeter minus A times the semi-perimeter minus B times the semi-perimeter minus C. So that's Heron's formula, and that's what we want to prove, okay? So here we go. Step 1. We're going to rewrite the law of cosine to isolate the sine of our angle C. Law of cosine does not have a sine in it. Sorry, I meant cosine of C. So up here, I am looking at this formula right there, and I want to rewrite it isolating cosine C. Now, we've already done that in some examples that we walked through, but let's just rewrite it. So cosine C equals, so it will be a squared plus b squared minus c squared all over 2ab. All right. Number 2, we want to rewrite the Pythagorean identity. So rewrite Pythagorean identity. And here we want to isolate sine of angle C. Okay, so we're going to go to the Pythagorean identity. We have it right here, right there. It is, you see it. And I want to isolate sine of C. Okay, so here we go. We're going to start with sine squared of angle C plus cosine squared of angle C equals 1. So I'm going to subtract the cosine squared. And now I want sine, not sine squared. So I'm going to take a square root. So sine of angle C is equal to the square root of 1 minus cosine squared C. Okay, now that I have this, I'm going to, let's see if I can, I'm going to remember that this is my cosine, right? I rewrote my law of cosine to have a cosine isolated. And I have a cosine right here. Granted, it's square, but I have my cosine right there. So I'm going to rewrite that cosine using a squared plus b squared minus c squared all over 2ab. Okay, so this is what I will use. And here we go. Let's change color a little bit so they don't all run together. Let's go purple maybe for a little while. So we're going to say sine of angle C equals the square root of 1 minus, and instead of having my cosine squared here, I'm going to have a squared plus b squared minus c squared all over 2ab, right? From right there. Okay, we're going to keep going. So now, that was my number 3. Now on number 4, I'm going to substitute that sign C in the area. So I'm going to take this expression I just came up with and I'm going to substitute it in the area formula of a triangle right there. Okay. So that will be the area is K is equal to 1/2 A times B, and then it will be times sine of C, but I'm going to replace my sine of C by that. So times 1 minus, and let's simplify something already. Let's say I'm going to square that denominator, not the numerator. The numerator I'm going to leave because it's quite ugly. A squared plus B squared minus C squared squared, but I'm going to go ahead and square that as 4a squared b squared. Okay. Number 5. I want now to take that coefficient that I have in the front, that 1/2 AB, and I want to bring it inside the radicand so that everything is inside my square root. So to do that, I would have to square everything, right? Because I'm putting it in a square root and it wasn't there originally. So I'm going to say, okay, then I have K equals 1, sorry, not 1/2 anymore. I want to take it inside. So what I'm trying to do, let me show you on the side first. What I'm trying to do is say that 1/2 AB is equal to the square root of 1/4 a squared b squared. Can you agree with me? If I take the square root of 1/4, I get 1/2. And if I take the square root of a squared b squared, I get my ab back, right? So I'm going from that form to this one so that I can include everything in my radical. Okay, so here we go. K is equal to the square root of, that inside will be 1/4 a squared b squared, and then whatever I had inside my radicand, 1 minus that ugly numerator, a squared plus b squared minus c squared all over 4a squared b squared. Okay, we are making progress slowly but surely. Now we are going to distribute, we're going to distribute this inside that radicand. So K equals distribute, so 1 times that will just be that, 1 over 4 a squared b squared minus that 4 and that 4 are becoming over 16, but the a squared and the b squared are going to cancel each other out. So I'm going to have a squared plus b squared minus c squared over 16, right? Because 4 times 4, that's 16, but the a squared, b squared, those are canceling each other out. Okay, so I'm here now. And what I'm going to do now is I want to get rid of this fraction. So I am going to factor out a 1/16. So I can get rid of my fractions. So I'm going to say, okay, 1 over 16. So if I do that, that means I need a 4 up here, a squared, b squared. And if you're not convinced, go ahead and redistribute that and see if you wouldn't get back that 1/4 a squared, b squared, right? You would. And then minus a squared plus b squared minus c squared. Oh, you know what? I lost something, didn't I? I lost my square up here. That quantity must be squared. That quantity must be squared. And that quantity must be squared. Okay, I think I'm good. Factored out the 16, right? So that will be it. Excuse me. Okay, so now we're going to take this out of the root here. And what else could we do? We're going to notice, okay, let's do that. So k equals, so that becomes a 1 over 4. And I'm going to rewrite that so that it's 2ab quantity squared, okay, minus a squared plus b squared minus c squared squared. Why do I want to do that? Because now I have something squared minus something squared, and that, ladies and gentlemen, is my difference of perfect square right there. Something squared minus something squared can factor into the conjugates, and so that's what I'm going to do now. So I'm going to factor that into two conjugates. So here we go. K equals 1 over 4, working in the root here. So my first term in my first conjugate will be 2ab, and then I would have plus whatever is inside that parenthesis. So a squared plus b squared minus c squared. That's the first one. And then I need the other conjugate, right? So that will be 2ab again. But this time I had a plus here, right? I'm going to show you we had the parentheses here, and the plus. So now I'm going to need the minus and the parentheses here, a squared plus b squared minus c squared. And now I can just distribute this negative, get rid of those parentheses as well. So k equals 1/4. And I'm going to rearrange those a little bit. So I'm going to have a squared plus 2ab plus b squared minus c squared. That's my first one. I just rearranged what was inside, and now I'm going to distribute this negative and rearrange the inside here. So distribute the negative will make it a negative a squared, negative b squared, and a plus c squared. So I'm going to say, okay, then c squared minus, and then I want my a squared minus b squared. Oh, no, I don't want that yet. I want to rearrange it differently. Sorry, guys. I know where I'm heading. That's why. I want that 2ab first. Then I'm going to do my minus b squared here, right? And that would rearrange that. Okay? Now, why did I do that? Because look at what you have here. Can you look at that? And can you look at that? And recognize our, where are they? Right there. Our perfect square trinomials. You see them? This one and this one. So we're on that side and here, and we want to rewrite them so they look like that and like that. Okay, so we're going this direction. So here we go. We'll change color again a little bit. Let's do green. So k equals 1 over 4. And this again is going to become my a plus b quantity squared, and then my minus c squared. And then the other one is going to be c squared minus, and then that factor will be a, oh, I think I have a sign issue somewhere. Where is my sign issue? Can you see it? I don't see it yet. Oh, no, I don't. I'm factoring out that negative, right? Factoring out that negative. So that was a minus a squared becomes a positive a here. That will be minus right there. So that becomes minus b squared. Okay, somewhere I'm not happy with what I have. It's because I want to write it this way. So this becomes positive. This one will become negative. And this one will become positive. By putting those parentheses and taking that negative out, it will change those signs. And then I can say, okay, that's a squared minus b, a minus b quantity squared. Okay, now we're good to go. All right, now we're back to conjugates, if you notice that, right? We have something squared minus something squared. That's a conjugate. I mean, the difference of perfect square, that's going to become conjugates. So we're going to have k equals 1/4. So those two are a difference of perfect square. So the conjugates are going to give me a plus b minus c times a plus b plus c, right? So a plus b minus c times a plus b plus c. Okay, that's one of them. And now I'm going to do the same with that. That's a difference of perfect square, right? Something squared minus something squared. So we're going to factor that as c minus a plus b and c plus a minus b. Okay, I hope I didn't mess up here. So c plus a minus b, because I'm going to have the conjugate of that, and that negative will be distributed. So that changes here and there. Okay, I think I'm good to go. Good to go. You can pause the video and recheck if you're not quite convinced. All right, so where are we going now? So we have all of that. Now we're going to go to our formula for the semi-perimeter. That's the last one we haven't used yet, right? Oops. So where is my formula? Right there. The semi-perimeter formula right there is what I'm going to use now, right? So I know that S is equal to 1/2 A plus B plus C, and I want to rewrite it so that I use, so multiply both sides by 2S is going to be equal to A plus B plus C. So I want to use that version of it. And I'm going to do a little bit of margin work first. So in the margin here, I'm going to say, okay, so 2S is equal to A plus B plus C according to the semi-perimeter formula rearranged, right? Okay, so when I'm looking at what I have here, well, that right there would be my 2S. But this is not quite 2S right there. So I'm going to have A plus B, and I want a plus C here, but I had a minus C. And so because I added that plus C, I need to subtract another C. And then that will be equal to 2S, right? So again, I had a minus C here. So that's my minus C there. But I want a plus C for my semi-perimeter formula. So I add C and then I subtract it right away again so that it doesn't change what I had. But now I need to simplify that. So that will be A plus B plus C minus 2 of those, so minus 2C, and that will be equal to my 2S there. So again, this one is going to be A plus B plus C minus 2C, which is going to become 2S, right? That's your 2S minus 2C. S, this is that, and then minus the 2C. So that's what I already did here. Okay, changing color because they run together. Let's go green. So now I'm going to go with this one, right? So for this one, I already have a positive B and a positive C, but I have a negative A. So I wanted an A plus B plus C, but I had a minus A here, and I added a positive A, so I need to do minus 2A. And that will be equal to, so that's now my 2S minus 2A. And finally, the very last one right there is going to be, I have my positive A already. I don't have a positive B, so I'm going to add that, and so therefore I'm going to have to subtract one from here. And I had my positive C already, but I still had my minus B there, okay? So that will be the 2S again, and then minus 2B. And that will be this one. Okay, so now let's rewrite our formula with everything we have. So this formula will then be K equals 1 over 4 square root of this here we said was equal to 2S minus 2C that one was just plain old 2S. This one we said was equal to, where is this guy? I had a positive, yes, this one, right? Because I had to subtract 2A. So that would be this one right there, 2S minus 2A. And then finally, the last one will then be this one, 2S minus 2B. All right, so we rewrote everything. We noticed that we have a factor of 2 kind of in a whole bunch of places. So we're going to take that out. Okay, so 1/4. I'm going to factor out the 2 from here. And I have that 2. I'm going to factor out the 2 from here. And a 2 from the last one. So we have K equals 1 over 4. 2 times 2 is 4, times 2 is 8, times 2 is 16. So we have 16. And now I'm going to reorganize that and I'm going to keep it alphabetically. But I want this one first because this one doesn't have any minus anything. So that's going to be, remember, I factored out the 2, right? So my 2's became my 16 here, right? So now I just have that S left. And then the S minus A, since I want to go alphabetically. And then the S minus B. And then the S minus C. And there is no special reason why we want to go alphabetically, just that it's down the alphabet, right? And it makes kind of looks cleaner. The square root of 16 I know to be a 4, so that can come out as a 4, but then 4 over 4 will cancel, right? So that will cancel with that. And therefore the area, when I have 3 sides given to me, is going to be equal to square root of s times s minus side A times s minus side B times s minus side C, where s is your semi-perimeter. And that, ladies and gentlemen, is the proof of Heron's formula. All right, that was a long one, 30 minutes, but it was worth it. It's a beautiful, beautiful work of mathematics right there. I'll see you in class.